Alright, ladies and gentlemen, today in this lesson we are going to talk about two new separation methods, and specifically we are going to talk about industrial separation methods. So you might remember from chapter 2 that we have discussed filtration, centrifugation, distillation, evaporation, but now we add two more. I want to start with adsorption. And adsorption, this is when something adheres, so it's not absorption. You should really pay attention to the D. What we can do with this, we can remove gases or we can remove colorants from a solution, for example. This can be important because, for example, if you work in a factory, well, they are making some kind of chemicals and very harmful gases are produced. You want to place like a filter that captures away most of the harmful gases. And to do that we have active carbon. Actieve kool, or just koolstof. This is a little bit modified, so it can take up much more harmful substances. It is also used in, for example, gas mask. That is another example. You can have these water bottles with a carbon filter that makes sure that you can drink water straight from a river. It is used a lot in wastewater treatment facilities, cat litter boxes, to take away the nasty smell of the cat poo. Those are a couple of examples. Now I will show you how it works, and I will do this with this red liquid. What we are going to do, we are adding a little bit of carbon, so we don't need a lot of carbon to take away all of the colorants. Just a little bit of carbon, and we just quispool. I don't know what the word is in English. So I think most of the colorants are taken up now by the activated carbon. Then we have to bring it over into a different test tube, and for that we have to make a filter, because I want to filter the solution and I want to see whether I have a clear and colorless solution in the end. So how did we fold the filter paper again? First one time double, and then another time take 3 sides to one end, one side to the other end, and place it in the filter. You can add a little bit of water just to make sure that it sticks to the sides of the funnel, and place it inside a different empty test tube. So now I will pour in our liquid and we'll see what happens. Well, this is awkward, just waiting. Oh no! Oh, it is still red. I think we might have not used enough activated carbon. So let's do it again, I guess. Alright, I'll just shake really vigorously to make sure that all of the colorants are adsorbed. I'm so lucky that the cleaning guy is singing all the time. Now second try. And we're back. As you can see, well, still not all of the colorants are removed, but it is quite clear. There also might be a problem with my filter. So if you are going to do this in one day, please try it over and over again until you get what you expect. So bad experiment, Mr. Boltjes. This separation method is based on, so the principle is based on how well the substance adheres to the adsorption agent. So let me just write that down. So this is the principle that it is based on. So if you remember, if we had evaporation, the principle is based on the boiling point, the difference in boiling point between two substances. For adsorption, it is based on how well the substance adheres to the adsorption agent. In this case it was activated carbon. Alright, let me move on with the next separation method, and this is chromatography. Chromatography, I have used that a lot when I did my studies as a pharmaceutical scientist. I did biopharmaceutical sciences, and for example, when we made a drug, a medicine, like paracetamol, we wanted to check whether we actually have made the pure substance or not. Using this chromatography paper, we can check whether we have the pure substance or maybe still some of our reactants from the beginstoffen. And I will demonstrate that using these colored pencils. Now you can choose which one you want. Blue, okay. Red, oh fine. And what? Okay. And we need a little bit of this chromatography paper. I think this would be fine. And I also expect you to look in the book and not just follow everything I say. The principle what this is based on is we have our mobile phase. This is the water. I use demi water in this case, but it might as well be ethanol, so alcohol, or any other substance. But what you have to make sure is we are going to put a couple of dots of the things that we want to examine, and then the eluent, the loopvloeistof, so that was the water that was in the beaker, it will go up this paper and it will take the substance that we have put on it and it will create a nice stain. And we can also see whether this red is just pure red colorant or maybe there are different colorants in this pencil, and then we would get different stains here, because each stain has a characteristic pattern, because some colorants they adhere better to the paper and dissolve less well in the eluent, in the water, and some other colorants they adhere not really to the paper and they dissolve really well in the eluent, so they get very high and very high, very high and very high. You should put a starting line here, not too high, not too low, because when we are going to place the paper inside the beaker, we do not want the substances that we are researching, we do not want them to already be in the water. We want the water to go up and take the substances through the paper. You have to do it with potlood, because otherwise you will get just like one big smear. Let me just put 3 dots on this paper with the pencils that we are going to research. Alright, so I put these 3 little dots here, and now I will just place this paper inside our mobile phase, inside our eluent. I will write all these words on the board when we wait for the chromatography to complete. So now we'll just wait. I was just talking about the stationary phase. And the stationary phase, that is the chromatography paper. Oh, it says paper, I'm sorry. Then we also have the mobile phase, and this is called eluent. And in Dutch we call this the loopvloeistof, because it elopes. That was weird. This separation method is based on 2 principles. How well the substance that we are examining adheres to the stationary phase. And the second one, how well our substance dissolves in our mobile phase, in our eluent. Alright, so the chromatography has finished. Let me show you the result. So as you can see, the red one completely dissolved. There's nothing at the starting line anymore. And we can see that the blue one actually consists of light blue. It's a little bit purple. Let me just explain how we can use these chromatography papers. We have just seen we get something like this. This is not very nice. We do not see very clear spots. Well, usually you see more clear and separated spots. So for example, I can get this here and this. So that might be 2 colorants. For this one I get this, and for this one I get this, this and this. So all different substances, and they are nicely separated. I can calculate that's called an RF value, and the RF value is typical for a substance in a specific eluent. loopvloeistof. How can we calculate the RF value? Well, we should take this distance, and this is distance B, and that is the distance from the starting line, so that is the place where we put the dots, all the way up to the solvent front. So this is how high the solvent has eventually gotten. Then if I want to calculate the RF value, let's say for this one, I should pick the distance to the center of the spot. Then I can calculate my RF value by dividing the distance to the solvent front, by dividing it by the distance to the center of the spot. Now a different example. What we can use this chromatography paper for is, for example, if I have just made paracetamol, I want to test whether that is pure, of course, because I want to test whether I can give it to people. So I'll put my paracetamol here, and this is my sample. It's a sample of what I have made. Dus een monster noemen we dat in het Nederlands. Then I want to compare it with something. With what do I want to compare it? Well, first of all, I want to make sure that I have made actual paracetamol. So my reference should be pure paracetamol. By the way, the order in which I do this is not really important. Then I can place a third dot. I do not want to place too many dots because then it can get a little bit messy. The third dot could be a starting substance. So if I want to know if my reaction was complete, then I can test if in my sample what I made is still some of the starting substance. And let's just imagine that I get this. I get my sample, I get this, and this, and this. Where for my reference, I get this. And then my starting substances, I get this. So what can we say about this now? Well, I see we have a spot at approximately the same RF value. So I can say, well, I've actually made paracetamol. But if I look at my sample, I can also see that there's a spot that is corresponding to the one with the pure substances. Therefore, my sample is not pure. And I can also see a third spot, which indicates that there even is another substance. So, this paracetamol, not pure. Alright you guys, this is the end of the video. I hope you've learned something. If you have any questions, please post them under this video. I will make sure that I answer them. And I wish you all best of luck with homework. Ciao.